am from the Buddhi Academy. So today we'll continue with the chapter that is structure of atom. So in today's class we'll see about the Rutherford's nuclear model of atom, atomic number and atomic mass, isobars and isotopes, and what are the drawbacks of Rutherford's model. So in our last class we have seen about the J.J. Thomson's atomic model, right, where it was considered to be a watermelon, where there is a positively charged sphere and electrons are embedded in them. This is what Thomson had given. Now let's see what Rutherford has proposed. So what Rutherford did is he did the nuclear model of atom. So Rutherford's nuclear model of atom. Now Rutherford and his students, he didn't perform this experiment alone, he performed it with his students. So what is the name of his students? That is Hans Geiger and Ernest Marsden. So these are the two students of Rutherford. So Rutherford with his students, what he did, he bombarded very thin gold foil with alpha particles. Now what are alpha particles? Those are alpha particles. They contain two protons and two neutrons. As in it is considered to be two nuclei of helium. Helium, you know, so it is considered to be two nuclei of helium. So Rutherford and students, what they did, they bombarded the gold foil with alpha particles. So Rutherford's famous alpha particle scattering experiment is, so this is what he did. So Rutherford scattering experiment, source of particles, alpha particles. From here, alpha particles were there. Then there is a lead plate through which the alpha particles are sent, and this is the gold. This is the gold foil, and this is a photographic plate. Photographic plate means whenever it strikes, the responses are taken here. This is a photographic plate. So these alpha particles, it strikes the gold foil and it reaches the end point. But when it strikes, there are various particles that are scattered. So these are all the scattered molecules. So this is what Rutherford's scattering experiment is. So beam of alpha particle, thin gold foil, some of them they go straight, whichever it's, some of them they go straight, some of them are deflected. So this is deflected alpha particles, you can see. So some of the alpha particles are deflected. Now, Rutherford's alpha particle scattering experiment is here it is represented where I showed you. So a stream of high energy alpha particles from a radioactive source was directed at a thin foil of gold metal. As I said, this is the source of alpha particle through which a thin beam of radioactive alpha particle is sent, which is striking on the very thin layer of gold foil. So this thin gold foil has a circular fluorescent zinc sulfide screen around it. So this photographic plate, it is the zinc sulfide plate, okay? It is the fluorescent zinc sulfide. When alpha particles struck the screen, a tiny flash of light was produced at the point. So whenever the alpha particle strikes the zinc sulfide foil, a flash of light appears. Okay, that is the indication that the alpha particles have reached the end. So the results of scattering experiment were quite unexpected. According to Thomson's atomic model, the mass of each gold atom in the foil should have been spread evenly over the entire atom. So what Thomson had said ki all the positively charged molecules, they are evenly spread in a circular form and the electrons are just embedded in them like watermelon, as I said. So according to Thomson, this is the thing. So according to Thomson, the golden atom in the foil should have been spread evenly. That's what Thomson had said, right? So and alpha particles had had enough energy to pass directly through such a uniform distribution of mass. If it is the way Thomson had said that that everything should be evenly spread. If it is like that, then the alpha particle should be directly passing through it, right? Because it is in a uniform distribution of mass. If it follows the Thomson's model, it was expected that the particles would slow down and change direction only by a small angles as they pass through the foil. And it was expected कि Rutherford thought कि this is okay with the Thomson's model. So he went to check the Thomson's model, right? Whether it is correct or not. So according to Thomson's model, this was what he expected because it is evenly distributed. So there should be very less deflections of particles. There should be small direction changes, right? And the particles should slow down. But it was observed that most of the alpha particles pass through the gold foil undeflected. So according to Thomson's model, it should deflect and slow down. But it was observed the straight opposite, that most of the alpha particles were passing through it. Okay, undeflected. A small fraction of alpha particles were deflected by small angles. Here, as I showed, most of them are passing straight, right? Most of them are passing straight. And a very few of them, that is this one and this one, very few of them are deflected by small angles. A very few alpha particles bounced back, that is, were deflected by nearly 180 degree, and very little, there was negligible, of them were reflected back 180 degree. 180 degree means if it is moving this way, they have turned this way in the opposite direction. So very few were deflected nearly 180 degrees. So on the basis of the observation, Rutherford drew the following conclusion regarding the structure of atom. So on the basis of this, he drew another conclusions regarding the structure of atom. So most of the space in the atom is empty. So what he said, what Thomson said, it is entirely covered with positively charged thing, evenly distributed positively charged thing, and then there is some electrons present in them, right? This is what Rutherford said, Thomson said. But when Rutherford performed this experiment, it was proved that it is not like this. So what conclusions he made? He made that most of the space in the atom is empty. He said it is not like this. There are empty spaces in the atom of the alpha part as the alpha particles pass through the foil undeflected. Because why he said there are spaces? Because most of the alpha particles, they pass without deflection. Okay, that's why he said that there is empty spaces in the atom. A few positively charged alpha particles were deflected. The deflection must be due to enormous repulsion force, showing that the positive charge of atom is not spread throughout the atom as Thomson has presumed. So what? There were few positively charged alpha particles which were deflected, right? Alpha particles, they are two protons and two neutrons. So they are positively charged, right? They are not electrons, they are protons. So they are positively charged. So few of positively charged particles were deflected, as we can see here. These are the few particles, those are deflected. Thus, the deflection must be due to the enormous repulsion force, showing that the positive charge of the atom is not spread throughout the atom, as Thomson said. So what Thomson's model said ki the positively charged thing is evenly spread throughout the atom. If so, then there should be repulsion because like charges attract each other, unlike charges repel each other, right? Or it is opposite. So it is like charges repel each other and unlike charges attract each other. So proton will repulse, right, each other. They will repulse each other. So there should be enormous repulsion between them if it follows Thomson's model. an atom follows Thomson's model, then all the alpha particles should be deflected, right? But here there is no deflection seen. Only few of them are deflected. That means it is not evenly spread throughout the atom as Thomson had presumed. So this is one of the drawback of Thomson's model, where the protons are not evenly spread on the atom. So the positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particle. So wherever this deflection is seen, at that particular place is the where protons are present. So those are not evenly spread, those are segregated in a point. Okay. So calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. So when Rutherford calculated all these values, what he found was that the volume occupied by the nucleus, means the space occupied by the nucleus, is negligible, because atom is very small, right? You can't see it with your naked eyes. That small atoms, nucleus, it is obviously negligible. You can't even make out, right? So negligibly small as compared to the total volume of the atom. So the radius of the atom is 10 raised to minus 10 meter, while that of the nucleus is 10 raised to minus 15 meter. So it is even smaller than the atom. So one can appreciate this difference in size by realizing that if a cricket ball represents the nucleus, then the radius would be about 5 kilometer. Now if you want to see it in a bigger large scale thing, because these are in different values, right? 10 raised to minus 10 and 10 raised to minus 15, so you can't make out. But if you want to make it out, you, you can draw a 5 meter of circle. Okay, 5 meter of circle, so it is obviously around your cricket ground. 5 meter ka circle, and your cricket ball, if you keep it at the center of the ground, that is how an atom and nucleus will look. So it is so small from the atom. Okay. So on occasion, on the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. So on the basis of above observations and conclusions, he proposed the nuclear model of atom after the discovery of protons. So the positive charge and most of the mass of the atom was densely concentrated in extremely small region. This small portion of the atom is called nucleus by Rutherford. So what Rutherford said ki the positive charge and most of the mass of the atom, okay, most of the positive charge and most of the mass of the atom, they are densely concentrated in a extremely small region, and this small region he named it as nucleus. Okay? The nucleus is surrounded by electrons. Then he said ki this nucleus, it is later surrounded by electrons, that move around the nucleus with a high speed in a circular path called orbits. So he said ki the nucleus, around the nucleus, the electrons circulate in a around the nucleus, electrons that move around the nucleus with very high speed, and it follows a path known as orbit, and he named it as the orbit, where the electrons move around the nucleus. Thus, Rutherford's model of atom resembles the solar system. You know that solar system, it is the sun at the center, then all the planets, they revolve around the sun. Somewhat like this was the Rutherford's model, where nucleus is at the centers and all the electrons, they move around the nucleus in a circular path known as orbits, where nucleus plays the role of sun and the electrons that of revolving planets, as I said you. So electrons and the nucleus are held together by electrostatic force of attraction. Now how this nucleus and electrons are held together, he She said that these are held together by electrostatic force of attraction because of their movement. Now, what is atomic number and atomic mass or mass number? So, the presence of positive charge on the nucleus is due to the protons in the nucleus. Right? There are protons in the nucleus. As established earlier, now Rutherford said na, that the nucleus it is consisted of protons and other masses like neutrons and all, and electrons are revolving around it. So, the presence of positive charge on the nucleus is due to the protons. So nucleus will have a positive charge because it carries protons. As established earlier, the charge on the proton is equal but opposite to that of the electron, right? So if protons are positive, electrons are negative. So they are oppositely charged. The number of protons present in the nucleus is called atomic number. Now what is atomic number? It is the number of protons present in the nucleus and it is represented as Z. Okay, Z is atomic number. And what is atomic number? It is the number of protons present in the nucleus. Now for example, the number of protons in hydrogen is 1. In sodium atom, it is 11. Why 11? What is the atomic number of sodium? It carries 11 protons. That's why it is 11. Therefore, their atomic numbers are 1 and 11 respectively because they carry 1 and 11 number of protons with them. Okay. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons. So, to keep the neutrality, electrical neutrality, what they did, they said कि the number of protons equals the number of electrons. So both protons and electrons are present in equal number. If there is 11 protons, that means there are 11 electrons. Okay. If there are 8 protons, that means there are 8 electrons. So the number of protons equals the number of electrons to maintain the electrical neutrality. For example, number of electrons in hydrogen atom and sodium atom is 1 and 11 respectively. So the atomic number equals number of protons in the nucleus of an atom or number of electrons in a neutral atom. Okay, because number of protons equals number of electrons. While the positive charge of the nucleus is due to protons. The mass of the nucleus due to protons and neutrons. So the positive charge is because of the protons and the mass of nucleus is due to the protons and neutrons which are present together. Okay. So earlier protons and neutrons present in the nucleus are collectively known as nucleons. So earlier where the protons and neutrons present in the nucleus. Collectively together it was known as nucleons. Okay, the total number of nucleons is termed as mass number. So the total number of nucleons, how many protons and neutrons are present together, is known as mass number, which is represented as A of an atom. So mass number equals number of protons plus number of neutrons. So what is atomic number? Atomic number is the number of protons present in the nucleus. And what is mass number? It is protons plus neutrons. Okay. Together, these protons and neutrons are known as nucleons. So this is the mass number and atomic number. Now what is isobars and isotopes? So the composition of an atom can be represented by using the normal element symbol X. So we can symbol a normal element as X with superscript of on the left and side as the atomic mass A and subscript Z on the left side as the atomic number. So how it is written? X. On top it is the atomic, it is the mass number, and on down it is the atomic numbers. This is how a normal element is represented. Okay, so isobars are the atoms with same mass number but different atomic number. For example, so what are isobars? They are the atoms with same number, same mass number but different atomic number. For example, carbon and nitrogen. So on top we write the mass number, that is 14. So both are having mass number of 14, but their atomic number changes. Atomic number of carbon is 6 and nitrogen is 7. So these are isobars where they have same mass number but different atomic number. So these are isobars. Okay. Now what are isotopes? Atoms with identical atomic number but different atomic mass number are known as isotopes. So straight ulta of this is isotopes, where you have same atomic number but different mass number. Okay. So in other words, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. So it is because of the difference between, now isotopes are present, it is because of the difference between the so the difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. So it is basically because the number of neutrons present in the nucleus changes. Okay, that's why you have same atomic number but different mass number. For example, considering hydrogen atom, where 99.985% of hydrogen atoms contain only one proton. As we know, hydrogen is 1, right? So it will contain only one proton. So these isotopes are called protium, where it has one atomic number and one mass number. So this is protium. Rest of the percentage of hydrogen atom contains two isotopes. So the other ones they contain, so hydrogen atom contains two isotopes, where the where their atomic number remains same but their mass number changes. Okay, atomic number it remains same but mass number changes. For example, deuterium. Deuterium has, it is a form of hydrogen only. Deuterium has one atomic number but its mass number is 2. Then we have tritium. Tritium has one atomic number and 3 mass number. So these are the isotopes of hydrogen, where the atomic number remains same but their mass numbers changes. Okay, these are the isotopes. So the later isotopes is found in trace amounts on the earth. So other examples of commonly occurring isotopes are carbon atoms containing 6, 7 and 8 neutrons besides 6 protons. Okay. Now this is because of the number of neutrons, because mass number it is the addition of protons and neutrons, right? Protons plus neutrons form the mass number. So the changes in neutrons will cause the difference in mass number, but the atomic number will remain the same. And 18 and 20 neutrons besides the 17 protons of chlorine. So chlorine and carbon are the basic isotopes or commonly occurring isotopes besides hydrogen. Lastly, an important point to mention is regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Now to identify how many numbers of electrons are there, we should know how many numbers of protons are there, because number of protons equals the number of electrons. Okay, so that's why we have to determine the number of protons in the nucleus first. So the number of protons will equal to the number of electrons. So number of neutrons present in the nucleus have very little effect on the chemical properties of an element. So neutrons will not play any role with the if chemical properties with of any atom. It will only play role in their mass number. Okay, apart from mass number, nowhere else neutrons are used as a chemical properties, or it won't affect the chemical property of an element. Therefore all the isotopes of a given element show same chemical behavior. So therefore all these atoms, they will show same chemical behavior. They won't change. Only thing is that they will have different mass number, but their chemical properties will remain same. Okay. Now, what are the drawbacks of Rutherford's model? Okay, Rutherford's nuclear model of an atom is like a small scale solar system, as I said, where nucleus is like sun and electrons are the part of the or planets that revolve around the sun, right? So it is a solar system. It is kind of a solar system. Okay, it is like a small scale solar system with the nucleus playing the role of massive sun and the electrons being similar to the lighter planets. So first the Coulomb force, where KQ1 Q2 by R2, where Q1 and Q2 are the charges, R is the distance of the separation of the charges, and K is the proportionality constant. So this formula where K Q1 by Q2 upon R square, where Q1 and Q2 are the charges. Okay, these are the charges and R is the distance, and K is the proportionality constant between the electrons and the nucleus. So this is between the electron and nucleus. In mathematics, if we show it mathematically, similar to the gravitational force. So this is the gravitational force where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. So this formula resembles this one, where in place of mass we have charge. When classical mechanics is applied to the solar system, it shows that the planets describe well-defined orbits around the sun. So when we apply a mechanics, it is shown that the planets, it revolve in a well-defined manner around the sun. Okay. So the theory can also calculate precisely the planetary orbits, and these are the agreement with the experimental measurements, right? So if they follow the well-defined orbit path, you can calculate precisely the planetary orbits and their arrangements in an experimental measurements. Through an experimental measurement you can calculate, right, based on the theory. So the similarity between the solar system and nuclear model suggests that electrons should move around the nucleus in a well-defined orbit. So if we compare the Rutherford's model with the solar system, it should also follow the same pattern, right? Like planets, electrons should also move around the nucleus in a well-defined orbits. However, when a body is moving in an orbit, it undergoes acceleration. So whenever anything moves round and round, it will follow an acceleration. Even if the body is moving with a constant speed in an orbit, it must accelerate because of changing directions. So an electron in the nuclear model describing planet-like orbits is under acceleration. So according to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiations. This feature does not exist for planets since they are uncharged. So planets won't be affected. If they move in an orbit, there won't be any electromagnetic radiations because they doesn't carry charge. But electrons carry charge. They carry negative charge. So whenever a charged particles moves in an orbit, it produces acceleration. It will move in an accelerated way, right? So according to Maxwell, it should emit electromagnetic radiations. Therefore, an electron in an orbit will emit radiations. The energy carried by radiations comes from electronic motion. So, if Rutherford's model is correct, then according to Maxwell's theory, the electrons should emit a radiation. So, the orbit will thus continue to shrink. If it starts emitting radiations, the orbit will shrink, it won't remain. Like planets, they have well defined orbits. They will move in that orbit only. It won't shrink, it won't expand, it will be like that only. But in case of electrons, it is not possible because electrons are charged. They will start emitting radiations due to which the orbit will shrink. So calculation shows that it should take an electron only 10 raised to minus 8 seconds to spiral into the nucleus. So if in case of electrons, if they start moving in an orbit and start passing the radiation within 10 raised to minus 8 seconds, it will merge with the nucleus. Okay, but this does not happen. But it does not happen, right? If that happens, then the atom will not be there. Thus, the Rutherford's model cannot explain the stability of an atom. So, therefore, Rutherford's model, it cannot explain the stability of an atom. If the motion of electron is described on the basis of classical mechanics and electromagnetic theory, you may ask that since the motion of electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary around the nucleus? So take if we delete the part that electrons are moving around the orbit and just make it that they are present stationary, like they are not moving, they are just present there, then according to the theory, classical mechanics and electromagnetic theory, you can consider it to be a perfect model. So if the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electrons towards the nucleus to form a miniature version of Thomson's model of atom. So if it is in a circular motion, it will eventually emit radiations and spiral around the nucleus. But if it is kept stationary, if it doesn't move and stays there only, then there will be electrostatic force which will act, which will pull the electrons towards it, and that will lead to the miniature version of Thomson's model where electrons are embedded inside the nucleus. So another serious drawback of the Rutherford's model is that it says nothing about the electronic structure of atoms, that is how the electrons are distributed around the nucleus and what are the energies of these electrons. So Rutherford, he didn't mention anything about the electronic structure of atom, that is how the electrons are distributed. It can't be like random distribution. There should be some distribution criteria, right? So he didn't describe any of those criteria, and the energies of these electrons are not mentioned. So these are the drawbacks of Rutherford's model, which led to the Bohr's model. So we'll see about Bohr's model in our next class. So I hope you have understood what we have done today. So thank you for watching my video. Please do like, share and subscribe to our channel.